Thank you, Chairman. I'm Sean from Korea University, and I'm pleased to be here at the hot city of Beijing. Because my message talk is the last one, I hope it's the last but not least. And today I'm going to talk about I/O latency issues in Xenon virtual machine. Actually, there is Xenon is a ARM port for Zen. It supports credit scheduler, SCDF, and split driver, and it has small footprints. Because with the help of split driver, it secures access from malicious or compromised domain. And actually, there is a controversy that Xenon is suitable for embedded systems or not. And one of the major reasons is the I/O latency. And it's so sad that Xenon's architecture inherently has some major drawbacks for I/O latency. And today I'm going to present how those I/O latencies are presented and how they can be mitigated using different approaches. Actually, the I/O latency issue is very important in mobile communication systems because if the I/O latencies are not guaranteed, then your phone call may be missed or dropped, and your network connection will be lost or taking a long time to detect your network. Unfortunately, current Xenon's I/O latency is not good enough to sufficient surpass the commercial networks. Because two major reasons are, first, lack of schedule support. It sticks to hierarchical scheduling nature. That means hypervisor schedules only vCPUs, and it doesn't schedule the task inside the guest operating system, so it cannot provide very strict time bound for every single task. And it is widely known that the current credit scheduling in Zen doesn't match to time-sensitive application, especially when the domain has mixed workload that comprises of I/O and CPU-bound jobs. And secondly, latency due to the split driver model makes this I/O latency problem more worse. In split driver model, all the I/O operations are performed at separated driver domain on behalf of the user guests. So even though the driver domain fails, the entire system can survive. So it can enhance reliability. However, it degrades performance with regarding to I/O latency because it requires additional I/O domain switching backend support from the user domain to the I/O domain. So we investigate these issues and some remedies for that. So the background, most of you may know about this. The credit scheduler is a weighted round-robin based fair share scheduler, and it has three priorities: boost, under, and over. The basic policy is to preserve fairness among all vCPUs. Each vCPU gets the equal amount of credit periodically, and the credit is debited as CPU consumes its execution time. And the scheduler basically picks vCPU that is understate in order to keep the fairness among them. And if the remaining credits if there is a remaining credit, then the state is under. That means underutilized. so the schedule picks one. Or if the CPU consumes all this credit, then the status priority is over. So when the priority is over, then CPU is not selected by nature. And it introduces boosted priority for providing long response time because of the credit scheduler's weighted round-robin based scheduling. It takes a kind of long latency, round-trip latency in terms of response time. In order to mitigate the long response time, the credit scheduler designers introduced a new priority boost called the boost. And the vCPU is boosted when the vCPU gets an IO event. So it seems like to deal about the latency issues. However, there are misconceptions in the boost priority. It's commonly understood that vCPU is always boosted by IO event. However, in fact, boost is sometimes ignored because the vCPU is boosted only when it doesn't break the fairness. So we call that case not boosted vCPU. So, for example, we can consider about the situation when a user domain has CPU jobs waiting for its execution and takes IO event. It should be boosted as prescribed. However, it doesn't because it primarily focuses on fairness. So it is waited for a short amount of time, and it will be executed soon. And tentative boosting is easy to break the fairness, so the vCPU is not boosted. And the second misconception about boost is it is not a kind of prioritized mechanism. Boost doesn't always prioritize the vCPU. Actually, in fact, boost is easy to be negated because multiple vCPU can be boosted simultaneously, and multi-boost happens quite often in split driver model. For example, when a driver domain when a network packet comes in, then the driver domain is boosted in order to take the network packet at the driver domain. And that user domain is also needs to be boosted. So at that situation, driver domain and user domain compete for the physical CPU. And another example, we can consider about the network packet comes in and goes to multiple virtual machines. Then all the designated virtual machines are boosted at the same time, so they compete. And there is difficult, almost impossible to guarantee high latency in that kind of situation. So here is the observed IO latency we have observed in actual practical system. You can see that red region shows some hypervisor levels code to driver domains code. The latency from Zen hypervisor to driver domains netback handling code. It is handled, in most cases, it is handled very short time. You can see this is kind of cumulative distribution graph. You can see 97% of interrupts are handled arrived at driver domain. However, you can see that there is still large worst case latency for some 3% of interrupt handling. And the second range is netback to DOM union latency. It is observed, it shows that considerable delay in most cases. So, in usual Zen situation. One is 84% instruments are handled in 1 millisecond. So, among them, multiple those number of